Hello everyone and welcome back to this lecture series on remote sensing. Unlike traditional technical lectures, this series introduces synthetic aperture radar known as SAR and polarimetric synthetic aperture radar known as PolSAR concepts using minimal yet essential mathematics. The goal is to help you grasp complex ideas without being overwhelmed by equations, making it perfect for developers and applied researchers entering the domain. In the previous session, we explored what remote sensing is, how it works, and why it's such a powerful tool in observing our planet. Today, we are taking the next step, diving into SAR and PolSAR. These radar-based systems allow us to see the Earth in ways that optical sensors simply can't, even through clouds at night or under forest cover. Before we begin, if you haven't already, please subscribe to the channel, click the bell icon and share this video with your friends or colleagues interested in remote sensing. So let's get started. This is the overview of today's lecture. First we will see what is SAR and SAR image formation. Then we will see common image distortions. Due to geometry, SAR images can show some inherent distortions known as foreshortening, layover and shadow. After that, we will learn about polarimetric synthetic aperture radar, followed by polarization channels and various PolSAR modes. Now we will see how actually microwave remote sensing works. The figure 1 shows the direction along the path of the radar is known as azimuth, and across the path of the radar is known as range. The resolution in both the directions should be very high to get proper information of the target. You must have studied that for a high resolution you need longer antenna. Will it be possible to send such a long antenna in space? The answer is no. So here also, to achieve very high resolution in azimuth, a very narrow beam is required. To get a very narrow beam, extremely long physical antenna is necessary. It is very difficult to build an antenna of several kilometers in length and operate from space. Therefore, synthetic aperture radar, which is also known as SAR, was developed to overcome the limitation of keeping long antenna in space. SAR systems use an antenna of much smaller physical dimensions which sends pulses from different positions as the platform advances, simulating a synthetic aperture by integrating the pulse echoes into a composite signal. This is shown in the figure 2. Here you can see the SAR is collecting the SAR is collecting the information of a sheep from different locations A, B, C and D. After acquiring the data, SAR will integrate it into a composite signal. Aperture means the opening used to collect the reflected energy that is used to form an image. In the case of camera, this would be the shutter opening. For radar, it is the antenna. SAR can provide better resolution than conventional real aperture radars. By proper post-processing, important information can be extracted from the high-resolution image acquired by SAR. The advantage of using SAR is that the spatial resolution is independent of platform altitude. There are few disadvantages of SAR. The viewing geometry of a radar results in certain geometric distortions on the resultant imagery due to its side-looking nature. The radar is fundamentally a distance measuring device. Slant range scale distortion occurs because the radar is measuring the distance to features in slant range rather than the true horizontal distance along the ground. This results in a varying image scale moving from near to far range. Although targets A1 and B1 are the same size on the ground, their apparent dimensions in slant range, that is A2 and B2, are different. This causes targets in the near range to appear compressed relative to the far range. So this is a near range, this is a near range, and this is a far range. Okay. Using trigonometry, ground range distance can be calculated from the slant range distance and platform altitude to convert to the proper ground range format. This conversion comparison shows a radar image in slant range display here, okay, where the fields and roads here are compressed and the same image converted to the ground scale display with the features in their proper geometric shape. Radar foreshortening and layover are two penalties which result from relief displacement. Figure 1 and 2 shows the foreshortening effect. When the radar beam reaches the base of a tall target like mountain, tilted towards the radar before it reaches the top of it, foreshortening will occur. Again, because the radar measures distance in slant range, the slope A to B will appear compressed and the length of the slope will be represented incorrectly, that is A dash to B dash. Okay, so depending on the angle of the hillside or mountain slope in relation to the incidence angle of the radar beam, the severity of foreshortening will vary. Maximum foreshortening occurs when the radar beam is perpendicular to the slope such that the slope, the base and the top are imaged simultaneously, C to D, as shown in the figure. The length of the slope will be reduced to an effective length of 0 in slant range, that is C dash D dash. Okay. The figure 2 shows the radar image of a steep mountain terrain with severe foreshortening effect. Okay. The foreshortened slopes appear as brighter features on the images. Now in figure 3 and 4, you can see it's a layover effect. Layover occurs when the radar beam reaches the top of a tall feature like a mountain. Here it is shown as a alphabet B. Before it reaches the base, that is shown by A, the return signal from top of the feature will be received before the signal from the bottom. As a result, the top of the feature is displaced towards the radar from its true position on the ground and lays over the base of the feature, that is B dash to A dash. Layover effects on a radar image look very similar to effects due to foreshortening. As with foreshortening, layover is more severe for small incidence angles at the near range of a swath and in mountainous terrain. Both foreshortening and layover results in a radar shadow. Radar shadow occurs when the radar beam is not able to illuminate the ground surface. Shadows occur in the downrange dimension behind vertical features or slopes with steep sides. Since the radar beam does not illuminate the surface, shadowed region will appear dark on an image as no energy is available to be backscattered. As incidence angle increases from near to far range, so will shadow effects as the radar beam looks more and more obliquely at the surface. The image shown illustrates radar shadow effects on the right side of the hillside which are being eliminated from the left. Now you know that we are using microwave band of electromagnetic spectrum for microwave remote sensing. There are various frequency bands as shown in figure 1. In microwaves, like P, L, S, C and X band, which are used for imaging. P has maximum wavelength, so it can penetrate more than X, which has minimum wavelength. Each band gives us different information about the same target. There are different satellites for different bands. The new satellite NISAR, which is recently launched by NASA and ISRO, has two frequency bands L and S. So, it can acquire the information of the same geographical location for both the bands at the same time. Electromagnetic waves have two polarizations as shown in figure 2. One is horizontally oriented and other vertically oriented. The Polarimetric Synthetic Aperture Radar system uses these polarized components of electromagnetic spectrum. There are four combinations of polarization channels. HH stands for horizontal transmit and horizontal receive, which is also known as copolarized or like polarized. So you can see here the energy is horizontally transmitted. Okay, energy is horizontally transmitted and it is received also horizontally. That's why it is known as HH. Okay, the next polarization combination is HV. Okay, so energy is transmitted horizontally, okay, and received vertically. That is called as HV. This combination is called as cross polarized. VH stands for vertical transmit. So vertically it is transmitted and horizontally it is received. Okay, so that is known as VH. This combination is also known as cross polarized. And the last is VV. VV stands for vertical transmit and vertical receives. So the signal is the vertically oriented signal is sent and vertically oriented signal is received. Okay. If the transmitting and receiving antenna is same, then HV and VH gives the same information. So those systems are known as monostatic systems. Okay. Now there are two more combinations which are used by few satellites called as RH and RV. Okay. RH stands for right circular transmit with linear horizontal receive and RV stands for right circular transmit with linear vertical receive. Now we'll see what kind of polarization combination we should use for different applications. So HH is generally preferred for the study of soil moisture. It is less sensitive to water roughness than VV polarization. Hence, it is suitable for separating sea ice and water and also for ship detection. VV is used for studying the capillary waves on the water surface. So generally it is used for oceanographic applications. HV, that is a cross polarized, is useful for vegetation discrimination and biomass estimation. So with the help of HV, we can identify different types of crops or trees. The HV backscatter from water surface is much lesser than VV backscatter. So the HV channel is useful for detecting targets on the water surface that create multiple scattering, for example, structure of ship and ice deformations. Similarly, can be used to separate broadleaf from grain. Based on which polarization combination used by the satellites, there are three types of satellites. Full polarimetric or quad pole, which uses all four polarization combinations. Okay, so in full pole data we have HH, HV, VH and VV, all the four. Okay, Then next is dual polarize. Second is dual pole, in that either we can use a combination of HHHV or HHVV, okay, to collect the information. The third is known as compact polarization. In this, circular polarization is used. Full pole systems are very costly compared to other systems.